Hello everyone, my name is Ted Kremenek. Today I'm going to be talking about one of the applications that we have built on top of Clang. So it's going to be building on all the libraries that Steve talked about this morning. And that is a standalone tool that goes and analyzes your source code to automatically find bugs. So I'm going to start from a very high level, 10,000 foot motivation. And the idea is we like to find as many sophisticated bugs as possible using compiler techniques. And the motivation for this comes from a real far away legacy. And that is when we use compile time warnings. For example, here's a check for the format string of a printf function. When these warnings are actually fairly accurate, they can catch some very serious bugs very early on. So this is an actual diagnostic from the Clang command line driver. And just take a look at this report. It's actually very interesting. The compiler is very precise. It tells you exactly where the problem is. The format string is underlined. And the problem is that there's a format conversion in this format string that's just bogus. And so it's pointing you to exactly where the error is. Now, this error isn't totally interesting on its own, but think about the implications of this. At runtime, this would result in some kind of unpredictable behavior. It's just kind of undefined depending on what platform that you're on. But a static technique, invoking the logic of the compiler, which looks at your code before you even test it or ship it off to other people, can catch bugs very early on, very systematically. And these kinds of things is pointing to where the problem is, so hopefully the fixes are often obvious. So that's where we're coming from. But as we all know, compiler warnings are just inherently limited. And sometimes they're so limited that we often just ignore them entirely. Sometimes they're just bogus. Sometimes they don't tell us anything meaningful. But we like to take that idea of invoking the analysis power of the compiler, essentially, looking at our code in real detail to tell us something much more specific about what's wrong with our program. And the kind of bugs that we're interested in aren't just bugs that occur on a particular statement. So this is a very syntactic kind of check. But bugs that require a very specific set of events, a path through your code, so to speak, in order to occur. So these are things like memory leaks, buffer overruns, logic errors. Wouldn't it be great if we could just automatically find these kinds of bugs automatically? The only way you can find these now are, some tester finds them, Valgrind or so forth, but it requires a very specific test case and user experience to find these. So the benefits of static analysis is basically 3 points. First, you can get very early discovery of bugs, and I've said this before. Basically, the adage is that the sooner you find a bug, the cheaper it is to fix it. Once the code goes out the door, it's much harder to make changes without having large-scale impacts on the rest of your code. And so bugs caught early are cheaper to fix. They involve less labor. They involve less people. Static analysis is also extremely systematic. If you think about testing, the only way that you can find a bug is actually have a particular test case that happens to trigger the route through your code to the actual problem. But static analysis is basically harnessing the compiler's inexhaustible attention to detail. It doesn't get bored. It just tries to reason about all the corner cases in which your code can be exercised. And this way, static analysis is very good at catching that code that might not run all the time, but when it does, it's just you just haven't adequately tested it. And the other thing is this is so important, finding bugs without test cases. Testing is really powerful, it's really useful. We have unit testing, we have all sorts of different ways to try and effectively test our programs. But some code is just really difficult to test. If you think about it like a device driver, you rely on having the device available and actually even running the device driver. And sometimes the events in order to trigger pass through your code depend on some external thing happening, like receiving a packet with certain kinds of data. Just think about all the infrastructure that has to be in place in order for you to actually test this code well. That said, static analysis is not a replacement for testing. There's a lot of bugs that it can't find because it just has essentially a finite amount of reasoning power. And I know this is all kind of vague, and this has become more concrete in a few minutes. So this talk is going to give essentially a high-level overview of this new tool that we announced last month at WWC, which we're just calling the Clang Static Analyzer. This name may change at some other point, but essentially to show that it's affiliated with the project. It's built as a set of libraries that are part of Clang, so it's built on the base libraries that Steve described. and it's driven by a command line driver that the user can use. So I'm going to give a brief demonstration of the tool on real code. Then talk a little bit more about the premise of how static analysis works, some more implementation details, go into the libraries a little bit, and talk about where we really like to go with this. So this technology is still very much in the early stages, and we're very excited with where it could go. And if you want more information, if you want to download it, it's a all 100% open source. Just go to the Clang webpage. So hopefully I won't have Nate's experience. Okay, cool. So I've got this directory. It's full of a bunch of C files which have very trivial case examples. It's not to dumb down things to show that it's not useful. It's just so that it makes it very clear what's going on. It contains a simple make file, so this could be any old project that you have. And it also doesn't depend on make. This could be like an Xcode project, Jam, or whatever. It doesn't really matter. So I could just run make, and it just builds everything. So there's nothing really magic going on here. So I'm going to do a clean build so that if I were to run make again, I would actually go over all the source code. And the way to invoke the static analyzer is that we run it through this command scan build. And all it does is it tells make, instead of just invoking GCC directly, to invoke GCC and the static analyzer. So both, the code is being forked off and analyzed by two different compilers, essentially. So it's pretty simple. And so the static analyzer will essentially see all code within your project, the same that your compiler sees. I'm going to add this -v option just so that it pops up a browser window showing me the results when it's finished. So this is a pretty primordial output at this point, but essentially this is an HTML file. It shows an aggregate of the results, the kinds of bugs that it had, the quantity. You can click through and toggle which areas you want to see. You can sort by line number, file, and so on. And so clearly, in order for these tools to be useful, you have to have a really good workflow around actually using these tools in practice. And this is really just kind of the early stages of what we think we can do. So is that big enough for you guys to see? So this is so again, these are really simple toy examples, but this kind of stuff actually happens very much in practice. So what's going on here is the static analysis tool is actually reasoning about specific paths through your code and the sequence of events that takes place. And it's giving you some diagnostics of the decisions it made and what it saw. So in this case, on line 9, we see that there's this if statement where P is tested against null. And at this point, the analyzer is assuming, well, since I'm not going to necessarily make any assumptions about P before it came in, but since you're actually testing it against null here, I'm going to assume that it could be null. And so then on the false branch, P is equal to null, and then it's dereferenced down below. Now with the power of the source location information we have in Clang, we can get very precise information about where the actual expression was and so forth. Now, I want you to pay attention. See, null is in red here. Null is actually a macro. And the really cool thing about integrating the preprocessor directly into Clang is that we can actually expand the macro definition right there, showing you exactly what the compiler saw. And this is a really simple macro, but these can get very complicated, and a lot of logic can be embedded in macros, and a lot of bugs come from this. So this is a really powerful kind of way to view your results. We're also not easily fooled by just simple castings. Here you're actually assigning the value of a pointer to a uint pointer t, so it's just the integer representation of the pointer. Then you actually test the value of that there, and then you assign it back to another pointer, and then you can actually see that there's a null reference there. So there's actually some fairly sophisticated value flow. And then here's just another one I think is very cute, returning an address of a stack variable. As you see right here, we actually say which variable it was that was returned. We assigned its address to y on line 5, and that's where we return it on line 7. We actually track which variable it was. So there's a fair amount of sophisticated reasoning there. And these kinds of diagnostics can be very effective at just telling you exactly what's wrong. So that's great. So how does that actually work? And again, the next few slides are going to be fairly pedagogical, just kind of giving you a flavor of what are the trade-offs in different kinds of analyses that we can implement in order to find bugs. So we can, from what we've seen from a lot of different tools like find bugs, Covarities Prevent, and so forth, there's a lot of different ways to find bugs with different degrees of analysis sophistication. And some bugs just happen on individual statements. You can find some of those bugs very accurately. I showed that with the printf example. Some bugs require analyzing, the scope of an entire function, like the ones I just saw. And others involve really doing some kind of deep analysis across the whole code base, looking how one function calls another, which calls another, and so forth. All these are important, and all of these require different levels of analysis time. And so some of them fall very naturally into different workflows, doing regular checking every time you build, or perhaps just as a nightly regression. Now I'm going to show you a trivial example of a check that we can do at compile time. It's a valid warning, and then show how it easily breaks, and give you an idea of when we have to actually crank up the analysis power. So this is a simple example where we have x declared at the top, and if y is 0, we actually don't assign it a value, and then we return it down below. Both GCC and Clang, as part of their standard compiler warnings, can emit a warning for this. Clang actually shows you the use of the variable. So this is actually an accurate error. And so what's going on here? So this is a source level control flow graph. We have these in the LLVM IR. Same analogy can apply to C. In Clang, we also have source level CFGs, which look essentially like this. And so what happens here is that both the compiler analysis sees this edge between the top block and the bottom. This is the path that I'm going to assume through the code, and x is not assigned a value at the top, and it's used at the bottom. So this is the path that it believes existed. Now, if I modify the code just slightly and add a guard on the actual use of x, it's almost exactly the same. The control flow graph just changes a little bit. But what's interesting now is if I run both Clang and GCC on it, they emit a warning, even though this is completely bogus at this point. And so this is one reason why people often just ignore these warnings, because at this point it becomes useless. It's just noise. So what is going on here? Well, essentially there's two feasible paths through this CFG. The first case is that both branches are taken, right? Because they're control dependent. If y is 0 at the top, it's 0 at the bottom. In the other case, that y is not equal to 0. It could be any value not equal to 0, which is fine. In that case, both branches are taken. Actually, both branches are taken. Now the problem is that the analysis being done by GCC and Clang, when they're just doing these very simple warnings, thinks that there's this path through this code. So it's just like magically the value of y suddenly, this is what from the programmer's perspective just changed, that the analysis isn't picking this up. And these kinds of false errors can happen very much in practice. And it's basically because they're not tracking the information from these branches. So we have a name for these things, and they're called false positives. They can occur for a lot of reasons. The one I just showed you is false paths, so just a path through your code that's just not feasible. And the other thing is that the compiler or analyzer or whatever you want to call it just has insufficient knowledge about what your program does, how it's being called from the outside world or whatever. And some of this information can be repaired by you telling it more stuff, but at the end of the day, it can only operate on the assumptions that it makes. And if it makes a false assumption, it can spit out noise. If you contrast this with testing, when you're testing code, you're actually really running it, right? So if you've recreated all the situations which the code would run in practice, a bug found by testing is a real error. So we got a lot of ways to reduce false positives. The biggest way is to just crank up the analysis, and I'm going to talk about the implications of that, and that's actually gone into what we've built. But it's just difficult to eliminate them completely. So what do normal compilers do? There's actually a name for this. And this might be pedagogical. I'm not certain how many of you know this. But essentially it's called flow-sensitive analysis. It's where the compiler can reason about the flow of values through the program as they're being executed. But it doesn't keep track of information from paths. So if you think about these guards here, it doesn't know about, when it gets to the plus plus x, it doesn't actually have any information about what x is. LLVM's SSA form with its phi nodes and so forth is designed essentially for doing efficient flow-sensitive analysis. And what happens with a phi node is that at the end of this branch, you're going to actually merge information here, right? That's how you don't get an explosion of information. The great thing about these is that they're fast algorithms. They can be used by optimization and compiler warnings. And this is really important because we want our programs actually to compile in some reasonable amount of time. But it's not always great for finding bugs. So what we've actually implemented is what we call path-sensitive analyses. And that's actually where you track information from the branches. And that can get arbitrarily complicated. So here, if you track the information from the branch, that you know that the value of x and y is either they're both 1 or they're both 2. And so you basically have this disjunction of facts from each one of the possible paths. And if you actually track information this way, the false positive that I showed earlier with the uninitialized value warning vaporizes. So that's the real motivator. The problem is that once you start tracking all these individual paths, you get essentially this big blow up. And when you start executing loops and so forth, the problem gets even more unwieldy. But we've got lots of ways to deal with it, lots of clever ways to merge paths and so forth to actually make this tractable in practice. However, in the space of bug finding, there's two things we're willing to give up. The first is completeness. So we're going to bound the amount of work that we're going to do. So we might not find all bugs in your, we might not explore all the paths within the code. And the other thing that goes back to the false positive idea is soundness. We might not necessarily prove that your program is absent of bugs. And this is actually not something that's hardwired into our tool, but you have the flexibility to make this choice. This is something that in the compiler world you would never, when you're actually compiling code, you would never do. But the goal here is to find bugs in fixed code, not to generate machine executables. So in Clang, we've implemented engines to do both flow and path-sensitive analysis. And I'll show a little bit more of how that's actually been useful. So being that we're Apple or whatever, really interested in Objective-C code. So there hasn't been really a lot of static analysis tools built for Objective-C. And so we thought, well, what kind of bugs can we actually find in Objective-C programs, given that we have Clang and it can parse C and Objective-C. And so it doesn't really matter if you know anything about Objective-C, except it's just the language of choice to build iPhone and Mac apps. So it's kind of important. And it's basically just another version of C with OO extensions. The thing that matters here is that we have this kind of memory management model built into Objective-C where you have these reference counts that are embedded in objects, and that by program design, you're supposed to use these counts in a certain way to kind of guarantee an absence of leaks. So this is like something very systematic so that programmers can follow this and so their code is leak-free. So naturally, this is something that we can check with static analysis. You've also may have heard that Objective-C also supports garbage collection now. But like anything, you're retrofitting this technology into a 20-year-old language. There are many subtle rules you need to obey in order to guarantee that it works, and we can check those as well. So I'm just going to walk you through this idea of how we actually check these kinds of leaks. And the same principles apply to any other kind of API, like malloc and free, fopen, fclose, lock, unlock, whatever. There's all these, contracts, protocols, whatever, that we write and use all the time. A lot of these could be systematically checked in the same way. So, ignoring the syntax, basically on the top line, we'd allocate some string. And it has a reference count that the programmer is supposed to release. We then pass string to some method foo, and we don't really care what it does with it. Foo can add or decrement reference counts to it, but essentially the reference count that we know for stir in this scope, we're responsible for decrementing ourselves. And so it's this very localized way of thinking. If you see a certain amount of counts in your scope, you're supposed to decrement them. And that's exactly what we do on this last line. Now, if we actually drop this statement, we have essentially there's going to be a leak at some point. Maybe not right here. Foo may have actually incremented the count, but then later on there could be a leak somewhere else. And that's actually kind of what makes this a little insidious to find these bugs using a dynamic tool, because the leak can occur long after the problem where it actually occurred. So here's an example of a diagnostic emitted by the tool on an open source program. Now the bugs I've seen on Apple code are more interesting, but this is actually this is pretty common idiom. So essentially this array is allocated every time this method is called, and then on some branch condition they just abort. And because Objective-C doesn't have RIIA, there's just a leak here. They never decrement the actual count. And the nice thing here is there's this nice sequence of paths to say exactly what happened. You allocated this object. It's no longer used at this point. You never decrement it. You have this surplus reference count. It tells you exactly what happened. So how does that actually logically work? Essentially, there's this abstract type, this DFA that's being tracked by the static analyzer on a pointer value that's returned from a method call. And so you can, plug in your equivalent thing, like whether something's in the lock state and should be unlocked and so forth. So essentially, when an object is returned from an allocation, we say it's owned with a +1 count. You can increment and decrement the counts as much as you want. You decrement it to the point where there's no more counts anymore. You should consider it released. It may have actually not been released in this current, immediately, but you should no longer consider it available. And then any use of it afterwards is considered a serious error. And then a memory leak is basically any time you lose the reference to the pointer and it's in one of the blue states. So this is really simple, right? This is the same discipline that the programmer is thinking about. We've just enforced it into the tool. And there's similarly another state machine for cases where initially you don't have an owning reference to the pointer and you increment and decrement the counts. And so implementing this is actually not that hard once the base infrastructure is in place. And so we think there's a lot of traction in Clang to actually build a lot of domain-specific checks using this very simple kind of reasoning. Things I haven't talked about, there's other ways to do clever tricks in Objective-C, use memory pools, garbage collection stuff. We're obviously, thinking very hard about it. We can address a lot of these, and we're thinking about very much how do people use these rules in practice, just so to make the tool very useful. I showed earlier in some of my slides about, we're doing pointer tracking, so we're doing aliasing along individual paths, so you have very precise information of what points to what. And there's lots and lots of room for improvement. The thing I want to mention is this is basically all in the core infrastructure. So if you were interested in writing your own specific checks, you don't have to reinvent this wheel. So so far this has been very successful. We've been using this checker in particular internally at Apple. We announced it publicly at our conference last month. There's been a lot of downloads of it from the Clang website, and we know that there's been thousands of leaks found because they're very structured and very easy to find. So I'll just close with some implementation details. So why on earth are we analyzing source code, right? We have the LLVM IR, right? I mean, it's this fairly rich, low-level IR that has a lot of information, but it removes a lot of the other high-level guck that we might not care about. Well, the problem is that when we're finding bugs, you actually care about a lot of that high-level information. The first thing is that the point of all this is not to generate machine code, but to generate meaningful information that a user could use to actually go and fix a problem. If they don't know how to fix it, it's completely useless. And so we actually need all that rich source level information. We need information about macros. They need to know where the problem actually occurred, what file it occurred. At the LLVM level, all that is gone. And now, hypothetically, you can go and maybe correlate some of the debug information by analyzing LLVM IR. But it's just really hard and it gets intractable very easily. The other thing is the compiler makes a lot of decisions when it lowers things like for loops and function calls down to LLVM. The order evaluation of expressions can change and so forth. And so you can, if you really wanted to check for portability of your code, you can let the static analyzer actually make those decisions very lazily and say, I'm going to check all permutations in which you use something. So you can get a much more systematic checking of your code. You can't recover that after it's gone. So where does this reside? Steve showed this figure earlier today. So basically all resides in the analysis library, which is really supposed to be a toolbox to provide a base solver for doing data flow analysis and so forth, and also these checks. It's not highlighted, but we also use the rewriter to do those HTML diagnostics. Steve mentioned the rewrite library earlier for doing an Objective-C to C translation. But the way we actually generate those HTMLs, we just take the source code and insert HTML tags. We know exactly the extent of all the tokens and expressions and so forth, so we can just slam the syntax highlighting right in there, including the things for macros and so forth. So what does Lib Analysis consist of right now? It consists of some source level control flow graphs, so essentially the equivalent of the LLVM IR but at a source level. And so things like ternary operators, short circuit operations, these are explicitly represented at that level as well. We have a flow sensitive data flow solver, so you can do things like live variable analysis and initialize values, the basic checks that you would want to do in a compiler, but now you can do it at the source level. We have a path-sensitive data flow engine, which we've implemented on top of it, this memory leak checker. But it also, just as part of tracking values for paths, can find things like null dereferences, those stack errors, and so forth. And we think as we track more and more information, we'll be able to find buffer overruns. They'll just fall out from that basic value tracking. And we've also implemented a lot of different checks. Dead store checking, which depends on live variables, which can identify some insidious dead code, and a lot of basic API checks. And I want to comment is that implementing these is actually fairly simple. And so if you're interested in implementing your own checks, although you have to use the Clang APIs at this point, eventually we'd like to make it more scriptable so that you could express these checks even in a higher order thing like JavaScript. And the last interesting thing is that the static analyzer doesn't know that it's rendering to HTML. We have a separated interface for reporting bugs from actually generating them. And that's using essentially this diagnostic client interface. And it's basically implements a view of the bug reports. So instead of having HTML, instead we could generate maybe directly to an IDE or some other database or something like that. And so looking forward, there's a lot we want to do. We want to be able to continue to enrich the diagnostics. I'd like to do interprocedural analysis or start baking it over the next year. Implement a lot of checks. Add the ability for people to easily extend the system without understanding all the core guts of the analyzer. And have a lot more different kinds of analysis engines since there isn't just one way to do program analysis. And for more information, if you're interested in checking it out, go to clang.llvm.org. Some questions? Yes?
Hi, I think you're hinting at this with your scriptability thing, but am I to understand that your pattern and medium checker now is just hard coded with each path and source and some intermediate ASP or?
Well, you do. Well, you can do both a combination of syntactic and semantics checks. Basically, you say when the engine tracks basically like the state that you're in along a current path, and then let's say you want to check every time I call a specific function that there's not null or whatever. You actually interrogate what's the value of the expression being passed in.
So you're basically doing code, not some kind of formal declaration.
That's correct. That's correct. But the idea is that we'd be able to, with the scriptability, is have different ways to express that, have it dynamically loaded in, and so forth. But right now it's hard-coded as checks.
Are you looking at
You can, that's a flag right now.
Okay, so you can actually,
Yeah.
like, I'll let it run as long as it takes.
Not, we haven't added it to the command line, but we can do that. It's literally just a value that you set in the API.
Any work on parallelizing?
That's right. Sorry. So the idea was, can you tell the analyzer essentially to remove the bound on how much work you can? And I said that that's completely API specifiable, so you can let it run for as long as you want.
Right. Is there any work to parallelize the analysis?
Exactly. So the analysis is based on using a lot of functional. So the question was, is there any work on parallelizing analysis? A lot of the analyzer is built on using functional data structures, so it's inherently designed to be parallelizable. And actually, there's a lot of data structures that we added to LLVM, like an immutable map, an immutable set. They're very much inspired from Lisp and OCaml for doing functional data structures. Yes.
So one thing how you know at a higher level that something can't happen.
Yeah.
Something the code is, but I slow things down, apply it, so like this,
Yes, when you see an assertion, when it sees an assertion, it assumes that condition. If it can't prove that a condition is true, it'll assume that if the assertion succeeds, it'll pick up those constraints. Yeah. Yes.
So I was looking at your examples, and they're all pretty simple.
Yes.
And I was wondering if you traded on some non-trivial pathological C sources.
So there's a lot of things we've traded on here that I can't. So we've run it over PostgreSQL. So those numbers we had earlier today, we've run it over Nmap. I'm trying to think of other open source things that fall in those category. So things like that. I see. Yeah. We've run it over GCC. Now a lot of these projects have also been scanned using other static analysis tools too. And so we still expect to be some false positives on these pathological cases, and our goal is to reduce those as few as possible. You first.
Change the press false positives by annotating something false like
We are gradually adding more and more support for that for individual checks. So the answer is yes. The question is, can you suppress false positives by annotating source code? And I said we're on demand. We're adding individual ways to do that. As people say, so you file like a bug report and say, here's a pathological case, I want to silence it, I want to silence this way. The nice thing about Clang is we control the whole front end, so we can easily add the support in there. Yes?
I'm curious what you're doing for this. If somebody says, I'm going to do this from 0 to 1 million.
Right. So right now, so there's different, it's a very modular system, so we can change the policy and how we want to handle loops in different cases. Right now, we're just essentially unrolling them a certain number of times, but we like to also add at some point some induction variable analysis where you basically say at this point I'm going to assume that I is in this range, and so while you might only unroll the loop essentially a few times, you're summarizing the effect of many loops.
So one question, for example, would be that often the problems are on the boundaries, right?
That's right.
You check the outside.
That's correct. So the issue is how do we handle loops and how do we handle thresholds within loops? We're gradually working on that. Okay.
So the question of parallelizing this, are you worrying about parallelizing the parser, or is the parsing a small enough chunk you won't worry about it? And does Clang have ways you could actually do some sort of parallelization
Of the parser.
Yeah.
The question is, with parallelization, are we concerned with parallelizing the parser, or essentially where is the trade-offs with the parallelization? I think the highest cost is actually doing the path-sensitive analysis. With parsing, the goal is because Clang is built as a library, there's a lot of incremental work we can do to reduce the work with parsing and reduce it that way. It's hard to parallelize parsing of C code since so much of it depends on other parts of it.
But it makes it the opposite of factoring, for example, where most of the time parsing is very low effective.
Right. So thank you.